Number 11. A paleontologist uncovers a fossil of a saber-toothed cat. He finds a specimen has 15% of its original carbon-14, which has a half-life of 5,730 years. How old is the fossil? So maybe you noticed on the worksheet that you got in class that there's another formula for half-life, and it's this. We've got A equals I. So A is the final amount, I is the initial amount, times 1/2 to the power of T over the amount of how long the half-life is. So using this formula here, we're looking for how old it is. So we're looking for the time. And so currently it has 15% of its original carbon-14. So that would be 0.15 equals, of course at one point it had 100%. Then we've got 1/2 to the power of T, which is what we're solving for, over the half-life is 5,730 years. So now we need to work with this a little bit. I'm going to rewrite this as a log. So I'm going to have log base 0.15 of, by the way, this 1 times anything that doesn't matter, so really when I'm rewriting this I've already ignored that. So log base 0.15 of, oh dear, that was wrong. Log base, clearly my base is 1/2. Log base 1/2 of 0.15 equals T over 5,730. So then at that point we can take T by itself, because I will multiply both sides by 5,730. And when I do that, let's write this out first. So log 1/2 of 0.15. I can go to my calculator and type it in. So I'll have 5,730 times, I'll hit Control to get to the log, base 1/2 of 0.15. Hit enter, and I get 15,682.8. So the fossil, as we just discovered, is 15,682.8 years old. Number 12. Bob bought a boat in 1993 for $20,000, and it has decreased in value by 6.85% each year. What was the boat worth in 2006? Okay, so that's the formula. A equals B times 1 plus or minus R raised to the T. Okay, so we're looking for what was it worth in 2006. So that'll be our final amount. Our initial amount was 20,000. We have 1. It's decreasing in value, so that means we're going to have 1 minus that rate of 0.0685. And it did give us the time. So our time here, let's see, if we bought the boat in 2006, or in 1993, but it's now 2006, the difference in that is 13. So our time is 13 as well. Then we just plug that into the calculator, and when we do, we'll get the amount is 7,950.73. Okay, so that's the end of the calculator part, the graphing calculator part. By the way, be sure to look over exponential and logarithmic applications worksheet, that long worksheet front and back that has word problems and the solving problems, which is on the back, solving logarithmic equations worksheet. For additional examples, each of those problems is going to be a good practice for you for the test. Now let's go on to the non-graphing calculator portion of the test. And here we are. So no graphing calculator. Just a lot of algebra. That's okay, we can handle it. So log base 4 of 8 plus log base 4 of 32. We have like bases of 4, we're adding, so we can combine it into a single log by multiplication. So that 8 times the 32 is 256, and we think 4 to what power gives me to 256? Well, 4 to the 4th power is 256, so there's our answer. 14. Log base 3 of 75 minus log base 3 of 25. So we have like bases of 3. This time we're subtracting, so we can combine it into a single log by division. So log base 3 of 75 divided by 25 is 3. Now we think 3 to what power equals 3? 3 to the 1st power equals 3. So we're done. Next problem, log base 16 of 4 to the 2x. There's a couple of different ways you could think about solving this. One way would be, if I have an exponent behind a log, I can move it to the front. So I have 2x times log base 16 of 4. So I have the 2x in the front, and 16 to what power gives me 4? Well, 4 is the square root of 16. So a square root in exponent form would be 1/2. So 16 to the 1/2 gives me 4. So this in the end, 2x times 1/2 equals x, and that is the simplified expression. Log base 6 of 6 to the 5th. Okay, to simplify this one, you can know what the answer is instantly whenever you have a log of a base that matches what it's being taken of. So log base 6 of 6, that just equals 1. So in a roundabout way, that cancels. But if you're wanting to remember why, remember an exponent you can move to the front. So you have 5 times log base 6 of 6. Well, that thing just equals 1. So here we have 5 times 1, which is just 5. But if you want to take the shortcut of it instead of writing it out, log base 6 of 6 cancels out to 1, so you're just left with that exponent of 5. Number 17, 3 to the log base 3 of 4x. Again, 3 with an exponent of log base 3, essentially it'll cancel and you'll just be left with a 4x. And it's a weird way to think about it, because in the exponent you're thinking 3 to what power would give me 4x? Well, that would give you an exponent that then you would put on the 3 and it would still give you the 4x again. Shortcut, 3 to the log base 3 cancels. You're left with the 4x. By the way, that is different than 3 times log base 3 of 4x. That would not cancel. It's only whenever that log is in an exponent up here. So that would have to be in your exponent in order for it to cancel. So don't do that right there, okay? Only here. Next problem. Okay, so again, log base 232 to the 6. I've got an exponent, I'm going to move it to the front. So I've got 6 times log base 2 of 32. And I've got the 6 times 2 to what power gives me 32? Well, that's 5. So 6 times 5 is 30. So you can see how quickly these problems go. Number 19. This one looks a little bit different. I've got log base 3 of 1 over 3 to the 5th power squared. So I'm going to go ahead and take that 2 to the front like I've done before. So I have 3 to what power gives me 1 over 3 to the 5th. Well, if I ignore that 1 over part, and I say 3 to what power gives me 3 to the 5th, well, that would be 5. But we know to get 1 over that would be a negative exponent. So log base 3 of 1 over 3 to the 5th is negative 5. Don't forget that 2 in the front. So 2 times negative 5 is negative 10. There's our final expression. Okay, ln of e to the 2x plus 6. So we just talked about if we see something like log base 3 of 3 to the x, that thing would cancel and you'd just be left with x. Well, ln, remember, just log base e. So if you see something like this, Log base e is just ln, so that would cancel. So ln and e cancel each other out, and you're just left with the 2x plus 6. 21. Log base 8 of 1 over 64. So I'm thinking this is log base 8 of, so 8 squared would get me to 64, but 8 to the negative 2 would get me to 1 over 64. So log base 8 of 8 to the negative 2 is equal to negative 2. I know that looks a little different than how I've written it before, but that's just another way you can look at it. 8 to what power gives me 8 to the power of negative 2. So that negative 2 right there. All right. Oops. ln of 1 or log of 1. For each of these, this first one I've got log base e of 1. So e to what power will give me 1? Well, anything raised to the 0 gives me 1. And same thing here, I've got log base 10 of 1. 10 to what power gives me 1? 0. So basically, if there is a 1 sitting right here, that means it's just 0. Number 23, solve for x. Log base 5 of x minus 2 is less than or equal to 3. I'm going to start out by rewriting this as an exponent. So my base is 5. So if I have 5 cubed will be on this side and the x minus 2 will be on the other. But since we are switching from log form to exponential form, that's the inverse, so I need to change the direction of the sign. 5 cubed is 125. And then if I add 2 to both sides, I'll get 127 is greater than or equal to x. But I'm not done, because remember, we can never take the log of a negative number. This thing right here cannot be negative. So x minus 2 has to stay positive. It has to be greater than 0. So x must always be greater than 2. So I need to combine this and the 127 into one statement, so I'll get 2 is less than x is less than or equal to 127. Okay, let's fill in these blanks. I've got f of x equals negative e to the x plus 2 minus 4. And we want to figure out the domain, range, and asymptote. Okay, so I've got e to the x plus 2. This is an exponential function. And remember, the parent function roughly looks like this. Okay, where its domain was all real numbers. Its range was y is greater than 0, and its asymptote was at y equals 0. And that's just true for any of our exponential parent functions. So, looking at this, moving left or right won't affect the fact the domain is still all real numbers. However, the range is going to change a little bit because it used to be y is greater than 0. However, we've moved down 4, so the y values are going to have something to do with that negative 4. But notice that we've reflected it over the x-axis, so it will be y is less than negative 4. And everything moved down 4, so the asymptote is also moved down 4 as well, so it's going to be at y equals negative 4. So the fact that it was exponential told me that it was going to be all real numbers, and the fact that it moved down 4 gave me information about the range and the asymptote. However, on 25, we've got 2 times the ln, or natural log, of x plus 1 plus 3. So remember that log functions, the parent functions, were the reflection of the exponential over that line y equals x. So the domain was x is greater than 0. The range was all real numbers. And the asymptote was at x equals 0. And that was true for any log parent function. So on the domain, I have moved to the left one. So the domain will have moved to the left one as well. So what used to be at 0 is now going to be greater than -1. The range was all real numbers, and stretching it and moving it up 3 will not change the fact that it's still all real numbers. And the asymptote, since we moved to the left one, the asymptote that was at x equals 0 is now at x equals -1. So the range came from the fact that it was a log function, and then the domain and the asymptote came from the left and right shift of our graph. Okay, we've made it to the last problem. Identify the parent function. So we've got A, B, C, and D here, and this won't all fit on the screen at once, so just kind of remember which one was which here. So on this first one, notice that we have a vertical asymptote. So right away, because there's a vertical asymptote, which kind of parent function has a vertical asymptote? So we've got an exponential, a quadratic, a square root, and a log. Remember that L reminded me of a vertical line, so this is a log function, so its parent function is log base c of x. Number 2. So you can see we have a horizontal asymptote, and when x is 0, y is 1. That to me sounds like an exponential function which has a horizontal asymptote, and anything raised to the 0 power, if that is 0, then the whole thing equals 1. So because I have that point 0, 1 and there's a horizontal asymptote, that tells me that this is an exponential function. And then for the last two, remember that I have not used b, which was the quadratic, y equals x squared, and I have not used c, which is the square root of x. So in this first one, it's a parabola. This should be so easy at this point that you should know this shape. This is clearly y equals x squared, and that was option B. The only one that's left, of course, will be for this one, but let's just talk about y. It looks like half of a parabola turned on its side, and of course that would be a square root function. So the only choice that was left was C. That's it. Please, please, please write down any questions that you may have had during this video and let me know tomorrow in class, because that's what it's going to be all about. Study hard and good luck on your test that you're working for on Friday. Bye!